Hi everyone, welcome back to Dave's Math channel. This is my continuing feature on the Math Lovers book. I haven't made any of these videos in a few weeks. I apologize for that. I was on vacation for the last couple weeks and I didn't have access to my studio for making my videos, but now I do again. So I'm going to continue making them as long as I can, hopefully on a daily basis like I've been doing. But anyway, today I'm talking about, this is my second video on section 5.6 of the Math Lovers book, which is on cardinal numbers. And in my last video, I talked about finite cardinal numbers. In other words, the number of elements of finite sets. There's not too much going on with those. But now we're getting to something a lot more interesting, I think. I'm going to start talking about infinite cardinal numbers. In other words, cardinal numbers of infinite sets. And it turns out there's different sizes of infinite cardinal numbers. That's not at all obvious. This is something that the set theorist Georg Cantor discovered in the late 19th century. I'm going to go into this a lot more detail in the next few videos, but today I'm just going to talk about what are called countable infinite cardinal numbers, and there's a symbol for countable infinite. The smallest infinite cardinal number, which is called countable infinity, is written aleph null. I didn't put it on this slide, but it's the Hebrew letter aleph, which is the first letter of the Hebrew alphabet, and then there's a little subscript 0 to the right, but you'll see that later. But anyway, let's just start on this. So but a good example to start with is the natural numbers, also called the counting numbers. This is the first, just a set of numbers you usually learn when you first learn about numbers: 1, 2, 3, 4, 5, and so on. And I think you guys all know there's infinitely many natural numbers. There's no biggest number, which means that the natural numbers go on forever. I'm using the symbol capital N to denote the natural numbers, and like I said, we can define the cardinal number of the natural numbers, even though it's not finite. We can give it a name, and as a matter of fact, that's done. It's called aleph null, like I said, and it might be a little hard to see on the slide, but I do have a picture of the Hebrew letter aleph with a subscript of 0 to its right. I think on the second to last line. So that's the symbol we use to denote the cardinal number of the natural numbers. But now here's where things get a little bit weird. We can talk about other infinite sets of numbers, like the whole numbers. I mean, this isn't too much different from the natural numbers. We just add 0. So the way I'm denoting the set of whole numbers in my book, I call it W. W is almost the same as N. The only difference is W has the element 0 in addition to the positive integers, 1, 2, 3, 4, 5, so on. So you might say, well, it has one more element, right? Because you're adding 0. You're adding another element to the set of natural numbers, and you're calling this the set of whole numbers. So you might think that W has a bigger cardinal number than N. I mean, that would be true if they were finite sets. Every time you add an element to a finite set, the set gets bigger. I mean, that's just common sense. But it turns out that's not necessarily true when we work with infinite sets. And the reason it's not true here is because is what's called a bijection, and I talked about bijections already. Another name for a bijection is a one-to-one correspondence. So there's a function from W to N. Just let f of x be x plus 1. So in other words, f of 0 is 1, f of 1 is 2, f of 2 is 3, f of 3 is 4, so on. I think you can see this function's a bijection. It has an inverse where you just subtract 1. But what's important here is that it gives us a pairing. It gives us a one-to-one pairing between the set of whole numbers and the set of counting numbers or natural numbers. Even though the natural numbers doesn't have 0, we can still pair everything up in both sets. And that means that the cardinal number of the whole numbers has to be the same as the cardinal number of the natural numbers. Another way to say that as aleph null plus 1 equals aleph null. This looks kind of weird because obviously for no finite numbers, it's never true that you add 1 to a finite number and you get the same number back. But for infinite numbers, that can happen, and in particular, it happens for aleph null, the smallest infinite cardinal number. You add 1 to it, you get back this thing you started. So I think that's the first surprise. But then you can do even better than that, it turns out. Let's look at odd and even numbers. So again, the set of odd numbers. Now I'm talking about positive numbers again. Odd numbers are just 1, 3, 5, 7, 9, 11, so on. Even numbers are 2, 4, 6, 8, 10, 12, so on. Well, if you take both of those sets together, take the union of the odd numbers and the even numbers, it's pretty obvious that gives you all the natural numbers. That gives you n. So if I call the set of odd numbers O and the set of even numbers E, then that just says that O union E equals n. And their intersection is the empty set. Because there's no numbers that are both odd and even at the same time. So normally when you take the this is called a disjoint union, the union of two disjoint sets. Normally, if you're talking about finite sets, if you take the disjoint union of two finite sets, the cardinal number of the union is just the sum of the cardinal numbers of the sets you started with. That's pretty obvious. I mean, if we did numbers 1 to 10, it's pretty easy to see there's 5 odd numbers, 1, 3, 5, 7, 9, and 5 even numbers, 2, 4, 6, 8, 10, and certainly 5 plus 5 equals 10. That's true if you started with any finite set of odd and even numbers. But here we have an infinite set, all the odd numbers, at least all the positive odd numbers, and all the positive even numbers. And you might think, well, these are smaller sets than the set of all the natural numbers. Their cardinality has to be less than aleph null. Well, it turns out that's not true. The cardinality of both the odd numbers and the even numbers are both equal to aleph null. How can we see that? Well, again, we could do the one-to-one correspondence business. Let's start with the even numbers. That's an easier set to look at. So now I'm going to make a one-to-one correspondence between the whole numbers and the even number, or the natural numbers and the even numbers. 1, 2, 3, 4, 5, so on, and 2, 4, 6, 8, 10, so on. Just double each number. So you start with a set of natural numbers. You take any natural number you want, say 47, double it, that gives you an even number, 94. And so you could have started with any natural number and get an even number that way. That means that there have to be the same number of even numbers as there are of natural numbers. So in other words, the cardinal number of the set of even numbers, the cardinal number of E, is also aleph null. And I think it's pretty obvious that the cardinal number of the set of odd numbers is also aleph null, because we could do another one-to-one correspondence for the odd numbers. Just say, n goes to 2n minus 1. So 1 goes to 1, 2 goes to 3, 3 goes to 5, 4 goes to 7, so on. It's also easy to see that the odd and even numbers have to have the same cardinality, because you can pair them up, just pair up, n and n plus 1 if you like, 5 and 6, 7 and 8, 13 and 14, whatever pair you want. So they both have cardinality aleph null, and when you add them together, you would think that's aleph null plus aleph null. I mean, that's since this is, again, a disjoint union, you're adding the cardinalities, and then that gives you the cardinality of the natural number, which was aleph null. So another way to say that is aleph null plus aleph null equals aleph null. This isn't true for any positive integers. It's true for 0, but it's not true for any finite cardinals except 0. Another way we can write this is 2 aleph null equals aleph null. So you could add 1 aleph null, still get aleph null back, or you could double aleph null and still get aleph null back. So we've just proved those two very counterintuitive results. So, like I said, infinite numbers, infinite cardinal numbers behave very differently than we expect. We get some very counterintuitive results. That's why, a lot. It's funny. I learned this a long time ago. I used to study physics, and physicists hate infinity. This is a big difference between mathematicians and physicists. Mathematicians love infinity, and physicists hate infinity. And I think the reason physicists hate infinity is because I think one reason is because there's all these seemingly paradoxes associated with infinity. And mathematicians tend to like paradoxes. I do too. I mean, there's always ways to resolve paradoxes in math. You have to define everything very precisely. Once you've defined all your quantities, all the things you're working with very precisely, you can free anything of paradoxes that you want. I mean, if math had any fundamental paradoxes in it, it would fall apart. It would, so I mean, mathematicians don't like real paradoxes because that would make the whole foundation of math fall apart. But you only get what seem like paradoxes when you make some faulty assumptions. And I guess one of those assumptions is that infinite numbers behave like finite numbers. They don't. And I think that's one thing that's kind of cool about infinite numbers and infinity. You get all these seeming paradoxes associated with infinity, but I think that's part of what makes math really cool. And I think another reason physicists don't like infinity is because when you're dealing with measurable quantities in science, I think every measurable quantity has to be finite. It doesn't make sense to have a measurable quantity equal to infinity. So, science kind of studies different sort of things. I mean, the math involved in science is a little bit limited, and I guess one of those limitations is there's really no room for infinity in the sciences, at least the way they're defined today. So, I just thought I'd mention that. But we're gonna have more fun with infinity and infinite cardinal numbers in the next few lessons. So anyway, that completes my lecture for today on cardinal, countable cardinal numbers or cardinal numbers of the natural numbers and such like it. So anyway, thank you for watching. Long live math, and I'll see you guys next time. Bye.